Welcome to NPTEL course on fractals and multifractals. So, in this sequence we are discussing about the fractal interpolation functions. So, we have constructed the graph of a continuous function which passing through the given set of point can be obtained as a unique invariant set of certain type of iterated function system. This graph associated with the continuous function, that continuous function we are calling as the fractal interpolation function. By varying different parameters, the shape and the pattern of the fractal interpolation function will vary. In the last class, we have discussed the influence of vertical scaling factor with respect to the constant as well as the variable scaling, and we have discussed the iteration process of fractal interpolation function. So, as a continuation of the last lectures, in this class we are going to discuss a special type of fractal interpolation function called alpha fractal functions. So, in this lecture, by choosing special type of Qi, we are going to generate the alpha fractal function. Let us discuss. Now, the alpha fractal interpolation function is developed with the special choice of Qi as in the form of given here. We know that the fractal interpolation function f is generated by the fixed point of the operator phi. Phi of f we will get as f. For generating this fixed point, we have the certain type of iterated function system we need to construct. In the construction of fractal interpolation function, we need to take the Li function which controls the x axis and Fi function which controls the y axis. The Li of x is defined as Aix plus Bi, and Fi function is defined as alpha I times y plus Qi of x. If we have the data points x1 to xn, then here x2, x3 extra, then here our xi and here our xi plus 1. Let us go on. For each interval, we need to define one Li function, and in the Li function in the horizontal direction, the Fi function in the vertical directions. Then we need to take the composition of this one, that means we are defining Wi of x comma y as Li of x and Fi of x comma y. This A is taken as the ratio between the whole subinterval over the whole interval. This alpha is the pre-parameter which hovers in the range -1 to +1. Then by choosing different Qi, one can get the different type of fractal interpolation function, that alpha I determine the shape of the fractal interpolation function. In the previous example, we have discussed the Qi of x we have taken as the linear function Cix plus di, and also we discussed one more type, this is 1 and this is 2, we discussed in the quadratic form plus Cix plus di. When the Qi is taken as this form, the linear form, then it is called the linear interpolation function or affine interpolation function. This is the affine map, and the 2 it is taken as the quadratic form of the special form, this one, then it is called the quadratic interpolation function. Now, we are going to discuss Qi in the special form. The Qi of x is defined as q of Li of x minus alpha I of b of x. Note that here g of x and b of x are continuous function defined on the interval I. That means I is an closed interval x1 to xn, it depends on the data. Now we defining two continuous function on I, g of x and b of x, such that the g of xi equal to yi. G is a continuous function on I as well as g passing through the given set of data, and the b function also continuous on I and b satisfying b of x1 equal to g of x1 and b of xn equal to g of xn, whereas b and g are not identically same functions. So, in the end point the function b and the function g both are same, whereas in the remaining point both are not same function. Now, if you are taking qi as this form, we need to verify whether this satisfying the endpoint condition of fi of x1 comma y1 equal to xi and fi of xn comma yn equal to yi plus 1. Here not xi, sorry, this is yi. We need to verify whether qi satisfying these two endpoint condition. Let us check what is the fi of xi x1 comma y1, which is equal to in the form of here in the form fi form is given here. So, it can be written as alpha I time y1 plus qi of x1. Here if you replace qi of x1 instead of x as x1, one can get alpha I of y1 plus g of Li of x1 minus alpha I b of x1. Now, you can verify alpha I of y1 plus, we know that this Li satisfying two endpoint conditions. If you are substituting any endpoints with respect to any Li, that Li of x1 equal to xi and Li of xn equal to xi plus 1. So, here we will get g of xi minus alpha I b of x1 is equal to g of x1. So, actually what is the function g? G is for all the I belongs to this number nn, then g of xi equal to yi. So, alpha I y1 can be written as alpha I y1 can be written as g of x1, because if you are taking is1, then g of x1 equal to y1 plus g of xi minus alpha time g of x1. Then these two term will cancel, one can get g of xi, the g of xi is nothing but yi. So, that if you are applying f1 of x1 y1, one can get yi. So, if you are choosing the special form of qa as this one, this is the satisfying this condition, and similarly we need to check this function satisfying b1 of xn comma yn. So, we need to check alpha I of y plus qyn plus qi of xn. So, which can be written as alpha I of yn can be written as g of xn plus this qi in the form of g of Li of xn minus alpha I time b of xn. So, again this equivalently written as alpha I of g of xn plus this term equals x. If you are applying Li on xn, it will map to xi plus 1, Li of xn equal to Li of xi plus 1. So, here you can get g of xi plus 1 minus alpha I b of xn. Now, these two terms will cancel, one can get g of xi plus 1 which is equal to yi plus 1. So, if you are using this endpoint, this is satisfying this kind, and here we obtained f1 of x1 and y1, that means any fi of x1 y1 is goes to yi, and fi of xn and yn goes to yi plus 1. So, the special choice of this qi also satisfying the endpoint condition. Now, this iterated function system Li fi, the specific stuff of qi is like this one, generate the fractal interpolation function. Here that b of x, the function b is called the base function, as it shrink the fractal graph horizontally, and it can be chosen as any polynomial or spline obeying the equation 1. That means, in the endpoint b and g must be equal, whereas b and g is not an identically same function. Then the non-affine fractal interpolation function, because this iterated function system generate the fractal interpolation function. The non-affine fractal interpolation function generated by previous iterated function system name as the alpha fractal function. It is denoted as g power alpha. It is not raising the power g raising the power alpha, it is just a notation. It stands for the alpha fractal function, is the perturbation of given continuous function g. One can observe that here g is given as like this one. That means, if the data points are given, here x1, x2, x1 comma y1, that means if n number of points are given, then g is any continuous function on I which passing through this data point, Now, based on this g, and we are forming the qi function like this one, then we are obtaining the fractal interpolation by using this iterated function system. Therefore, the fractal interpolation function g alpha is the perturbation of the given continuous function g. Then the IFS for generating g of alpha consisting of three major things. One is a partition of the original function g. G is defined on the domain I. So, the partition of the domain here, that means the data point in the x axis, a scale vector associated with the partition, that means the vertical scaling vector alpha I in the each interval, mainly a base function depending on the endpoint of g, that means the function b. So, this g alpha is depends on the partition of I and the scale vector alpha I and the base function b. Now, consider the partition delta of the given data point. In the data point, we can take x1 as a and xn as b. Then consider this data point, the partition of the given data point, and to approximate the prescribed continuous function defined on closed interval a comma b to r, a family of fractal function g of alpha is invoked using this one. That means, we are approximating given continuous function by mean of fractal functions. So, qi of x can be in the form of g of Li of x minus alpha I times b of x. Here the base function satisfies the constraint, the endpoint b and g is same, whereas the both are not identically same function. Now, then the functional equation of g of alpha is expressed like this one, because if we are taking fi of x comma y in the form of alpha I times y plus qi of x, if you want to say that f is a fractal interpolation function. As we discussed, f must satisfying the fixed point equation like this one. Then what is this operator phi of f? The phi of f is the function f of Li inverse of x, comma f composition Li inverse of x. Now we are taking q of x in the special form of q of x in the special form of g of Li of x minus b of, we are taking g of Li of x and alpha times alpha I times b of x. This is the special form of q of x given in equation 2, alpha I b of x. Now if f satisfying this functional equation means that f of x can be written as this form, that this f form is given here. Therefore alpha I times y times f composition Li inverse of x plus qi of Li inverse of x, that means q composition of Li inverse of x. Now q in the form of this one here. Now you can replace q in the form of this one, then one can get alpha I f composition of Li inverse of x plus, instead of x you need to replace as Li inverse of x. Then if you are applying here, one can get g of x minus alpha I times b composition Li inverse of x. So one can get, if you replace qa of x as a Li inverse of x, one can get this form. Now here you can take the scaling factors common, then this equation becomes f minus b composition of Li inverse of x plus g of x. So this is our f of x. Now this fractal interpolation function we naming as a g alpha, just the notation we are taking g alpha of x will written as, maybe this g of x I am writing here, and plus alpha I time g power alpha g alpha minus b of b g alpha minus b composition Li inverse of x. Now that g of alpha, that the fixed point, that means the fractal interpolation for the given iterated function system will satisfying this functional equation. So one can get this equation. Fine. Now one can observe that from this one can get this one. You can observe that if alpha I is 0, then g alpha of x is written as g of x. By varying different alpha, we can get the different version of fractal interpolation function which approximate the g of x. Therefore we are giving the fractal interpolation in term of alpha. By mentioning this, we give the name as g of alpha. Now the function g of alpha satisfying this equation 3 is referred as the alpha fractal interpolation function of g. Now if the base function is taken as a composition of g with the continuously increasing function c satisfying c of x1 equal to x1 and c of xn equal to xn, that is b of x is written as g composition c of x. We know the behavior of g is passing through the given data set, any continuous function which we are going to approximate. Now the functional equation becomes g of x alpha I or alpha n of g of alpha minus, in term of b of x we are writing g composition c. Then here also if you are taking alpha as 0, then g of alpha equal to g, it means that the fractal interpolation function g of alpha, that means the fractal perturbation of g of alpha mimic the behavior of G when each scaling factor alpha I equals 0. Fine. Now, we will find the error bound between G of alpha and G. For finding the error bound between G of alpha and G, we can take this functional equation G of alpha of x equal to G of x plus alpha I times G alpha minus B composition LIN of inverse of x. You can take the G of x this side and use the supremum norm, because all the functions are continuous on the closed interval a comma b. Then with respect to this metric, supremum metric or maximum metric, it forms the complete metric space. Now we can use this metric. Now if you want to find the distance between this one, that fractal perturbation of G and the G, then take the supremum norm of G of alpha minus G, can take here, then which is less than or equal to modulus of alpha times modulus of, that means supremum of G of alpha minus G of B. Here this term denote the maximum of all the scaling factor. The alpha I has range -1 to 1. Here alpha is the maximum among all the alpha i's. Therefore, this term is less than or equal to this quantity. Now you can add the G function on here, adding and subtracting and using the triangle inequality. This is the metric, therefore it is satisfying the triangle inequality. It becomes less than or equal to this term G alpha minus G plus G minus B. Now here G alpha minus G and here we have G alpha minus G. One can take the left side and take this term as out, then one can get 1 minus supremum of alpha, that means the maximum of alpha I, times norm of infinity between G of alpha minus G is less than or equal to this term times this term. Now we need to find the difference between, that means the error between G of alpha and G. Then one can get this term is over. If you are taking this one, then one can get G of alpha minus G, the norm distance between these two is less than or equal to the maximum of the scaling factor over 1 minus maximum of the scaling factor times G minus B. The G is the given function and B is the base function. So one can get here, if we approximate G by the G of alpha, the error bound one can obtain by using this equation. Now we are going to define a fractal operator. As we mentioned here, if you are changing any alpha, we can get the approximation of G. Also, if you are changing this function G, one can get different type of fractal interpolation function. Now a alpha fractal operator is defined by f of alpha. This is the operator, is defined as C of I to C of I, where C of I is the set of all continuous function on the closed interval a comma b, where I is the data point interval, such that this f of alpha of G equal to G of alpha, because for every continuous function G on I which satisfying G of xi equal to yi, we can get the corresponding G of alpha. We can get the corresponding G of alpha. So this function, this operator maps, if you are taking one continuous function associated with the continuous function, we can find the alpha fractal function. So it maps the G to the G of alpha. Now if B of x we are taking as this form, where G is the continuous function passing through the given data and C is defined here, the endpoint, the C and G are same, whereas both are not identical function. The C is a continuously increasing function. Then B in the form, if we are taking like this one, then the norm of g minus b of alpha we can get like this one, which is less than or equal to 2 times norm of g. Then the f of alpha of g minus g, that means the bound between these two thing we can obtain by the previous result which we obtained, we can get this result. Now using the triangle inequality, here if you are applying the triangle inequality, then f of g can be written as adding and subtracting g with the f alpha of g, then which is less than or equal to this one, then you can apply this term, then one can get this term time this one. Now this can be reduced as, this term can be reduced as by simple calculations, then one can get 1 plus maximum of alpha I 1 minus maximum of alpha I, that means the maximum of the scaling factor is denoted here, norm of alpha times g of alpha. So which is bounded by this term. So this is the bounded operator, the fractal operator, this one is the bounded operator. Hence the g of alpha one can write as like this one. Now we will discuss the perfect example to explain the nature of alpha fractal function. For a given function g of x as the positive square root of x, the positive square root of x, let us take the set of data point. The data point is 0 and 0, 1 by 4 and 1 by 2, 1 by 2 and 1 by root 2, 3 by 4 times root 3 by 2 and 1 comma 1. You can observe, if you are taking these data points, we are taking 0 of 0, 1 by 4, 1 by 2, 3 by 4 and 1, 0, 1 by 4, here it is 1 by 2, here it is 3 by 4, here it is 1. Then we have the function square root of x, the positive square root of x, we are denoting as like this one. Then 0 goes to 0, 1 by 4 goes to 1 by 2, maybe here, and 1 by 2 goes to 1 by root 2, it is 1 point something here, and 3 by 4 goes to somewhere here, and 1 goes to 1 here. Then we can get the function like this one, those like this one. Now this is our g of x given here, and this is the data point. Now if you choosing the proper alpha I and the qa of x in the form of qa of x in the form of g of li of x minus b of x, alpha I times b of x, where now we need to choose this base function. For the base function, choose the scaling factor as 0.3 minus 0.4, 0.5 minus 0.3. In each subinterval we are choosing the different scaling first. We are choosing different scaling. Then the base function we are choosing the 3 different choices. First one is b of x equal to x. That means we are taking 0, 0 and 1, 1 the initial points. If you are substituting 0 as 0, you will get 0, and x as 0 you will get 0. If you replace x as 1, you will get 1. So line passing through these two line, if you are taking, then g of x 1, that means x1 equal to b of x1 one can get, as well as g of xn equal to b of xn one can get. If g of 0 and b of 0 is equal, and g of 1 and b of 1 also equal, we have taken like this one. And similarly we can take b of x as like this one and b of x as like this one. Now we have the alpha I and b of x is this one. Then what is the li of x? As usual, one can calculate li of x plus bi, and fi of x comma y is alpha I times y plus q of x we are taking as q of x we are taking in the form of g of li of x minus alpha I times b of x. Now if alpha you can replace here, then one can, here alpha I is given for each interval, alpha is given, b of x is given as x here, and g of Li of x, for g of x is given as root x. So, for each Li of x we get one part and root x, then we will get the iterated functions corresponding to this, each be a 3 iterated function system. It generate the fractal interpolation function like 3 different fractal interpolation functions. This is the red line shows the given function root x, and this function, the blue line, shows the alpha fractal function generated by the iterated function system with b of x equal to x, with the scaling factor alpha is given here 0.3 minus 0.4, 0.5 minus 0.3. For the next function, if the alpha is same, the data point is same and the g of x is same, just changing the b of x as this function, then one can get the alpha fractal function like this one corresponding with the root x is given here. Then the third choice, if you are choosing this function b of x as like this function, the product of ux and gx, where ux is cos phi x by 2 plus sin phi x by 2. If you are choosing this this function as u of x and g of x is a root x, then one can get the alpha fractal function associated with the root x is like this one. You can observe from here we are choosing the base function line joining these 2 points, then you are getting this type of approximation. When you are taking the base function as in terms of the exponential function, one can get like this one, and if you are taking the cos x, that means the periodic function, one can get like this one. And among all three, this is very close to the g of x. Also, by using the error bound, one can find the error between the two functions, that means g of alpha and g, we can find the error between these two functions. Also, these three functions, this g alpha of 1 I can call, this is g alpha of 2, this is g alpha of 3. These three functions are generated by the iterated function system, which previously we discussed. All the three functions are fractal interpolation function. You can observe, you can take any part of this function, it reflects the whole. Here also there is a take, it will reflect the whole, and here also then you can take the part, it will reflect the whole. Now what we did here, the function given as root x, that means this continuous function is approximating by the term of fractal interpolation functions. So if any continuous function is given, we can approximate by the fractal interpolation function by appropriate choice of base function and the scaling factor. So this can be applied for any continuous function which passing through the given set of data points. So in the classical interpolation also, we can find different interpolation functions for the given set of data points. For the given set of data points, we are finding the different type of continuous function. If we want to approximate this continuous function in terms of alpha fractal function, we can use the QI defined in this theory lecture, then we can generate the alpha fractal function corresponding to these continuous functions. So likewise, we can approximate any continuous function passing through the given set of data points by mean of the alpha fractal functions. Thank you. So one can refer this textbook, M.F. Bansley, Fractal Everywhere. Thank you.